In just over 10 years, we should only be driving electric cars. That's what the European Union wants. For this to happen, we need lighter and cheaper batteries for cars. Let's go into detail in this video about how EV batteries work to understand their advantages and challenges. Stay until the end to see why I believe that, even though the electric car market has slowed its growth, the future still belongs to them. Until the end of the video, dear friends, an announcement. I have been nominated for the Romanian Influencer Awards 2024 in the education category. On the list, you will also find other dear friends, Alex, Attention, Katmeri, Horia, Zayafed, or Dan Kadar in the tech category. So, you have someone to vote for. I like what I do. I can never say, that's it, I've learned everything. There's nothing left to find out. With your help, I keep learning too. I'm trying to put a link here somewhere on the card so you can vote, but I'll also leave the link in the description. I'm out of sync. A few years ago, when everyone believed in electric cars, I didn't believe. Today, when people are becoming skeptical, I'm optimistic. A few years ago, I used to tell people this. Car batteries are heavy, they're expensive, and on top of that, they don't work well at low temperatures. You'll end up stranded on the road in winter, I used to tell them, but they wouldn't listen. Electric car sales exploded, as you can see in this chart. In 2020, there were 3 million. In 2023, almost 14 million electric or hybrid cars were sold. But what I said wasn't nonsense. What is holding back this growth is electric car batteries. The battery of the Dacia Spring costs about 7,000 euros, weighs almost 200 kilograms and gives you a range of 200 kilometers. That's in the summer. In winter, much less. At 5 degrees Celsius. The range is only 80 kilometers and charging takes 13 hours at home. And if you have a fast charging station, it takes 1 hour. These numbers aren't very appealing to me. As a result, people are readjusting. The company Audi, which still wants to produce only electric cars by 2033, says that the transition will be slower. Meanwhile, they'll also produce hybrid cars. The same goes for General Motors. The reasons? 1. High prices. Usually for those with deeper pockets. At Tesla, the electric battery exceeds 20,000 euros. I have a Kia Picanto. It cost me 10,000 euros. 9. I read that a Kia EV9, the electric car, costs 50,000 euros. I think I'll pass. Another problem is the public charging stations. The United States would need 180,000. It only has 40,000. Fortunately, I have one. Right in the parking lot in front. Do you have one? To these concerns is added the usually low number of kilometers you can drive with an electric car on a single charge, which becomes even lower during winter. Buyers are growing skeptical. That doesn't mean the electric car market is collapsing. In 2023 in North America, 40% more electric cars were sold than in the previous year. In total, there were 1 million vehicles. And China, with its production of 5 million electric vehicles annually, is ready to take over the European market. How much of that will be allowed is another discussion. Where is the problem? As I anticipated, essentially the problem is in the batteries. Look, the electric motor is essentially much simpler than the combustion engine. We all agree on that. All kitchen appliances use electric motors. Otherwise, the car is made the same way. Body, seats, steering wheel, and so on. The difference is the energy source. The battery, electric energy, or the fuel tank, thermal energy. Batteries for electric cars have some intrinsic disadvantages compared to the gasoline tank. They have a lower energy density, both by volume and by kilogram. This makes the batteries bulkier and heavier. In addition, batteries charge more slowly than gasoline, which is poured directly into the tank. And let's not forget, electric batteries are still expensive, even though their price has dropped. As for the price of fuel, electricity, or gasoline, the difference is not very big, and it also depends on how prices evolve on the market. Why do batteries have all these problems? To understand, let's go back to how an electric battery is made. After that, I'll tell you why. Despite the disadvantages, I'm optimistic. Here is the Volta battery, the first battery made of zinc, copper, and a layer soaked with salt between them. It's called an electrolyte. How does it work? The electrolyte eats away at the zinc and releases some of its electrons. Then, some of the zinc ions diffuse into the electrolyte and reach the copper atoms. They give up some of their electrons to the zinc, which becomes neutral and no longer matters. Thus, at the interface with the electrolyte, two zones are formed. One with free electrons and another with positive copper ions, arranged near the electrons, if that's the case. When we place a bulb, a load between the two zones, the electrons can thus reach the copper ions more easily, through the conductor and the bulb in this case. A current is formed and the bulb lights up. The problem with Volta's battery is that it can't be recharged. How do rechargeable batteries work? Let's take the example of lithium-ion batteries, which are most commonly used in electric cars. And by the way, I like this headline from 10 years ago. Lithium is used because its valence electron is the most weakly held by the nucleus. The electron of hydrogen, for example, has an energy of minus 13 electron volts. That means you have to give the electron an energy equivalent to 13 electron volts to remove it. On the other hand, the ionization energy of lithium is 5 electron volts. If you want to steal its valence electron, lithium is one of the atoms from which this electron can be easily stolen. If the electron, you only need an energy of 5 electron volts. We say that lithium has a high electronegativity. It easily loses its electron. Here's the structure of a lithium-ion battery. On the left is a cobalt oxide crystal, which contains lithium atoms. On the right are layers of graphite, which can also be found in pencil leads, and in the middle is a specially designed separator. However, the crystal on the left has ionic characteristics. This means that in the crystal, lithium has already lost its valence electron and has become a positive ion. Watch what happens when we charge the lithium-ion battery. An electric field is created inside between the positive and negative sides of the power supply. What does an electric field do? It exerts a Lorentz force on the electric charges. Positive electric charges are pushed in the direction of the field, while negative electric charges are pushed in the opposite direction. In other words, this field separates them. Let's see now what happens in the crystal. The valence electrons of the lithium atoms, which were wandering around the crystal, so to speak, actually have a special role in the cohesion of the crystal, but we won't go into detail. So, the free electrons in the crystal are also influenced by the electric field. They will move the other way because they have a negative charge. They reach the electrodes, flow through the conductor, and then the electrons reach the graphite layer on the right. Here they settle roughly in a layer. On the other hand, the electric field also acts on the lithium ions and is strong enough to pull them out of the crystal. They thus diffuse to the right, pass through the separator membrane, which is specially designed to allow only lithium ions to pass, then reach the graphite and settle randomly between its layers. They stay apart from the electrons in the graphite, which they want to reach. Electrostatic attraction draws them, but the graphite structure blocks them. What occurs when we discharge the battery? The electrons still want to reach the lithium atoms they came from. They can do this by freely moving back through the electric conductor, thus generating electric current. However, this way they only reach the crystal where the lithium ions are missing. This is where solid-state physics comes in. The crystal was built in such a way that the energy of the lithium-ion and electron system is lower when they are part of the crystal than when they are separated in graphite. This means that the lithium ions will also return to the crystal because the total energy will be lower. Basically, the lithium ions easily diffuse back into the crystal they left through the membrane. These batteries are good not only for cars, they can also be used in photovoltaic systems. If you want to install such a system, try EcoSolaris. It is a company that offers state-of-the-art equipment and photovoltaic panels, helping you save energy. Choose efficient and durable solutions that guarantee optimal solar energy production. The professionalism and over 18 years of experience of the team ensure a fast and safe installation. This way, you will turn your home or business into an autonomous energy center. Also, the financial benefits are significant with notable reductions in electricity costs. With EcoSolaris, you will get continuous support and specialized consultancy, so you can have the best experience. Visit the ecosolaris.ro website now to find out more information. I'll leave the link in the description. Alright. How does understanding how lithium-ion batteries work help us? Well, it helps us see why countless improvements are possible in the future. In other words, why am I now more optimistic when it comes to the future of electric cars? Let's estimate together the energy density of a lithium-ion battery. How? Well, it's clear that the energy is stored in the lithium ions when they are separated. How much energy does a lithium ion release when it gains an electron? In electron volts, an electron volt is a unit of energy. The calculation is easy. We multiply the battery voltage of about 3.7 V by the charge of the ion, which is equal to the electric charge of the electron in absolute value. So a single ion gives us an energy of 3.7 electron volts. A lithium ion, however, is part of the lithium cobalt oxide crystal unit. The mass of this unit is 1.6 times 10 to the power of minus 22 grams. Then we use Wolfram alpha and divide the energy stored in a lithium ion, about 3.7 electron volts, by the mass of the lithium cobalt oxide crystal unit, which is 10 to the power of minus 22 grams. We express this in watt-hours instead of electron volts, and Wolfram alpha gives us an energy density of about 1000 watt-hours per kilogram. Wow, I didn't expect that. It's not far from the actual energy density of a lithium-ion battery in practice, which is about 200 to 300 watt-hours per kilogram. Of course, in practice, the density is 3 to 4 times lower than the theoretical value, for many reasons. We also have the separator layer. We also have the graphite, which adds extra weight. The energy density will become lower and lower. Plus, in practice, the lithium cobalt oxide crystal, the separator layer, and the graphite are placed on some foils which are then packed tightly. And these also weigh something. Plus, in practice, not all lithium ions diffuse toward the graphite. In fact, we can say it the other way around. When engineers manage to achieve an energy density only a few times lower than the maximum theoretical value of 1000 WkG, which we also calculated, that's truly extraordinary. Congratulations to them. Why is the above calculation important? Because it tells us not only what the problems of car batteries are, like low energy density, but also how they can be solved. It's true that a battery energy density of 200 Wk is low. To travel 500 kilometers without recharging, a car needs 80,000 Wkg. That means the battery can also weigh 400 kilograms. On the other hand, the energy density per volume of electric batteries is also lower than that stored in a gasoline tank. That means batteries take up more space than gasoline. And yet, my optimism comes from the calculation above. So, how can we increase the energy density per kilogram? By looking for a lighter crystal. How can we boost energy density per volume? By searching for and researching more complex crystals. How can we lower the prices of electric batteries? Well, we find a cheaper way to manufacture the crystal, which is a major part of the cost, or by finding other crystalline structures that have the same function but are cheaper to manufacture. I was going to give you examples of such structures because research in the field of electric batteries is booming right now. Then to show you examples of batteries that make it possible for electric cars to reach even 1000 kilometers on a single charge. Unfortunately, this video has already become too long, but I will do that in a future episode. Please leave me links to interesting materials in the comments. Until next time, I remind you that I have been nominated for the Romanian Influencer Award 2024 in the education category. Vote by clicking this link right here. I'll add the link in the description. Until next time, I'm Christian Presura, Physics Explained. You are cool and I wish you all the best. Goodbye.